this video, let's study about the invertible and non-invertible systems. So what are these invertible systems? The invertible systems are those where the distinct inputs will be producing the distinct outputs, or the input is recovered from the output. Suppose this is a system as I am applying the input x of t. Okay, the output of this particular system is y of t. Okay, so from this signal, that is y of t, if I can recover this original signal x of t, okay, then that is called as invertible system. So if the system is invertible, then the inverse system also exists. So I will consider another system here. Okay, so now the output of this first system is given to the second system. So what happens? This produces the output z of t. If this z of t is equal to our original signal x of t, then we can call that this is the invertible system, and this one will be your inverse system. So this is actually, see, if x of t is the input signal and z of t is output signal, and if output is equal to input, then we will call those systems as identity systems. Okay, so now if I am recovering this x of t from the output signal y of t, so this is your inverse system. What is this actually means? See, this system, it performs some operation on the input signal. Then only we get this signal y of t after performing the operation on the input signal. Now what does this inverse system do? What is its job? Its job is to undo the operation which was performed on the signal x of t. Okay, that means here whatever the operation was performed, it will be undone by the inverse system. Okay, so only what happens, we will be getting the original signal, that is x of t. So basically this will be used in the communication systems or in the digital signal processing. So for example, if I am transmitting the data over communication channel, because of the non-ideal frequency response, okay, what happens? The signal gets distorted. Now our job is to, okay, get the signal that is very close to the input signal, right? So that can be done using such systems. Okay, so it's used in the communication system, it's used in the digital signal processing also. So when we consider the rectifier, you know rectifier, okay, for full wave rectifier, what will be your output? Okay, it's like this, right? So what happens? Y of t will be equal to mod x of t, mod x of t. But this is non-invertible. Rectifier is a non-invertible system because the rectification process, it cannot be undone. Okay. So if I am getting the original signal back from the signal y of t, it is invertible system. Otherwise it is non-invertible system. So if the system is invertible, we also have the inverse system. Okay, that is what the second system was, the inverse system here, which was undoing the operation which was performed on the input signal. So let us take some examples now. Say x of t minus 5, x of t plus 7, 5x of t minus x of t. Okay, so these are what our linear time invariant systems, because these are linear also, they are time invariant also. Okay, so y of t is equal to x of t minus 5. So now I am giving the signal x of t as the input. The output will be our x of t minus 5. So by seeing this only, we will tell that this is the shifted signal. Okay, that means it is shifted towards right by 5 units. That means this is the delayed signal, right? Delayed signal. So what happened? So this system was performing the operation on the signal, that was a shifting operation. So it shifted right, okay, shifted right by 5 units. Okay, 5 units. Now what happens? We have to see, okay, whether it is whether there is 1-to-1 mapping. So for example, okay, another example, like to identify whether it is invertible or non-invertible. So here, if I give, if there is a system here, if I am giving an input like 4, okay, constant 4, if I consider, it is producing output 5. Okay, it is producing output 5. But if I am giving -4, okay, -4, this is another input. If it is producing the same output for both the inputs, then this is non-invertible. But if it is producing distinct, so for example, if I am applying the 2 input, I am getting 2. If I am applying -2 and I am getting -2 here, so for each input I am getting a different output, unique output is obtained. So this will be your invertible system. Okay, that means there should be 1-to-1 mapping. Suppose this one, y of 1, let me consider this is y of 2 and this is y of 3. So here from x of 1, x of 2, x of 3, if this signal, if it is producing this and this is producing this, this is producing this, there is no 1-to-1 mapping. So this becomes your non-invertible. But if it was 1-to-1 mapping like this, that is invertible. So there should be 1-to-1 mapping. So here x of t is equal to x of t minus 5. Okay. If I give the signal u of t, it is u of t minus 5. If I give minus of u of t, it is minus of u of t minus 5. Okay. If I give delta t, this is delta t minus 5. Minus delta of t, this will be minus delta t minus 5. Okay, so these all are distinct outputs, right? No output is same here. So it is distinct. So we can say this as invertible system. So if this is invertible system, then what is the inverse system of this? So to get back x of t, to get back or to recover the signal x of t, what I can do? This was shifted right by 5. Now I will shift it left by 5. Okay, suppose this is y of t, I'll call this as y of t. So if this is shifted, okay, y of t plus 5, it is shifted left now, right? So this was shifted right, now this is shifted left. So what happens? X of t minus 5 plus 5, that is equal to x of t. Okay, so this will be your inverse system. So if I consider it separately, okay, now if I consider x of t minus 5 as the input, okay, now I should get the output x of t. So to get that, what I will do? I will replace t by t plus 5. So t plus 5 minus 5, that will give you x of t. So we can say x of t plus 5 is the inverse system. X of t plus 5 is the inverse system. Okay. Next, y of t is equal to x of t plus 7. So here I am applying the input x of t. I am getting the output here y of t. Okay. So here what happens? By seeing this, we got to know that this is the advanced version of the signal. So it is shifted left by 7 units. Okay. This is shifted left by 7 units. Now to recover back the original signal x of t, what I have to do? I have to shift this particular signal right by 7 units. That means I must delay it now. Okay. If I delay it, this is y of t. So if I do it like this is equal to x of t plus 7, right? Now if it is y of t minus 7, I will be getting x of t. See, y of t minus 7, x of t minus 7 plus 7. This is x of t. Okay. So this is the inverse system. So if I consider this separately, this was your output. So x of t plus 7 is the input to this particular system, system 2 now. To get x of t, what I have to do? I have to shift it. So I will do t minus 7. Okay, x of t minus 7. So replace this t by t minus 7. Okay, I will be getting x of t. So x of t minus 7 is the inverse system of this. So these two were time shifting. Okay, these were two were shifting. So time shifting is not affecting the invertibility. So y of t is equal to phi x of t. This is nothing but this is the amplitude scaling. Okay, so this is the amplitude scaling. Now the input is x of t, the output is y of t, that is equal to phi x of t. So first let us check whether this is producing the distinct output or not. So suppose I am giving x of t as 2, I will be getting y of t as 10. Okay. If I give minus 2, I will get minus 10. If I give it as 0, this is 0. X of t, if I give it as 1, this is 5. So this is also producing the distinct output. Okay. So this is invertible system. Now if this is passed through a system 2, that is inverse system, I should get back the signal x of t. How will I get? That is 1 by 5, right? 1 by 5 of x of t. So 1 by 5 into phi x of t, that will give you x of t. Okay. So 1 by 5 x of t, it will be the inverse system. Next is mod x of t. So this already we know, the rectifier, the rectification process cannot be undone. So this one will be your non-invertible system, because say suppose x of t is equal to 1, y of t is equal to 1. X of t, if it is equal to minus 1, then also output will be equal to 1. So the same output is produced for the two different inputs. So this is a non-invertible system. Okay. This is non-invertible. Next is x square t. What about your y of t is equal to x square t? So see, this is your non-linear time, means it is not a linear time invariant system. Okay, because it's non-linear, so it does not come under LTI systems. This one also is not linear. Okay, that's why it is also not coming under the linear time invariant system. So x square of t, now let me consider x of t is equal to 1, y of t is equal to 1, x of t is equal to minus 1 whole square, that is equal to 1. Here also it is producing the same output for the different inputs. So this is also non-invertible system. This is nothing but a squarer, right? Okay, this is rectifier output. Okay, so these are non-invertible systems. Next comes x of 3t. This is nothing but the time scaling. This is also the time scaling. Okay, let us see now. X of 3t, that is equal to y of t. Okay, so if I give delta of t as the input, now let me consider unit step and the delta function, impulse function as the test signals. Delta of 3t, that will be equal to 1 by 3 delta of t, minus delta of 3t, that is equal to minus 1 by 3 delta of t. U of 3t, so you know scaling, it doesn't affect here, so it is u of t, output is u of t, minus u of 3t, it is equal to minus u of t. So we can say that, okay, this is invertible system because it is producing the distinct outputs. Okay, so this is invertible system. That means inverse system also exists for this. So x of t is given as the input to the system. I am getting y of t, that is equal to x of 3t. Okay, y of t is equal to x of 3t. Now to get back the signal x of t, okay, so it should be y of t by 3. Y of t by 3 is nothing but x3 into t by 3. Okay, where t is replaced by t by 3. So I am getting x of t. Okay, so this is the inverse system. So if I consider it separately, this is the x of 3t as the input. Output should be your x of t. So to get output x of t, what I will do? I will replace t by 3. So x of t by 3. Okay, so this operation is performed on the time variable. I will be getting x of t. So x of t by 3 will be your inverse system. Okay, that is your inverse system. X of t by 4. Okay, so this will also produce the distinct output. So same like this procedure. Okay, what will be your inverse system? This is producing x of t by 4. To get this is your y of t. So y of 4t, that will give you x of t. That means y of t is equal to x of 4t will be your inverse system. Okay, this I will get in terms of x when I consider this as separately. Okay, separately means here this is the input to this particular system. Then to get output, then you have to replace t by 4t. So this is your inverse system. Okay, inverse system. So what about your time reversal? Time reversal, x of minus t. Okay, so delta of minus t, delta of t if I consider, this is equal to delta of t, u of minus t. Okay, that will be giving you u of minus t. If u of t, okay, that is the test signals we are giving. So it is also producing the distinct outputs. Okay, this is also coming under the non-linear time invariant systems. Okay, so here this is also producing the distinct outputs. So if I give x of t as input, I am getting a y of t that is equal to x of minus t as the output. Now if I give this as input to the inverse system, I should get x of t. That means again I have to perform the reversal operation. Okay, so what happens? The t will be replaced by minus t, that will give you x of t. Okay, we have recovered the original signal. So x of minus t will be the inverse system. So next is y of t is equal to x of t plus 9. So this is also invertible system. Okay, this is also invertible system. You can put the different values and you can check. Okay, so if x of t, if it is producing the output y of t that is equal to x of t plus 9. So this is given to the inverse system. To get x of t, what I should do? X of t minus 9. Okay, so x of t minus 9 plus 9, that gives you x of t, right? So x of t minus 9 will be the inverse system. Next is cos x of t. This is inverse system. This is also invertible system. This is invertible. This is also invertible. Okay, these two are non-invertible. See, cos x of t. Suppose x of t is equal to 0. I am getting it as 1. X of t is pi. I will get minus 1. Cos of pi by 2. I will be getting it as 0. Okay. Cos 3 pi by 2, I will get it as 0. Cos 2 pi, I will get it as 1. So it is producing the same outputs, right? It is producing the same outputs. So this is non-invertible system. There is no one-to-one mapping. So next comes x cube of t. So this was x square of t. Now this is x cube of t. Suppose x of t is 1. I'll get y of t as 1. X of t is equal to minus 1. I'll get y of t as minus 1. X of t is equal to 2. Y of t will be equal to 8. X of t is equal to minus 2. Y of t is equal to minus 8. So this is producing distinct outputs. In this case it was not that, so that it was not non-invertible system. But here it is producing the distinct outputs. So I can call this as invertible system. Okay, this is your invertible system. So that means x to the power of nt, if n is odd, this is invertible. If n is even, this is non-invertible. Okay, this is an important point. Okay, x to the power of n, x to the power n of t. So now x of t is given as the input. I am getting x cube of t. Now if I perform the cube root of this x of t, x cube of t, I will get x of t. Okay, so this will be your inverse system. So next let us check this minus 5 by 2 x of minus 2 minus t. Okay, so this is also not a linear time invariant system. Okay, so minus 5 by 2 x of minus 2 minus t. Another technique to solve this is, see, we need not draw the block diagram every time. See, I will see here to get x of t, what all I can perform. First, I can perform the reversal operation. Okay, I can perform the reversal operation. So it is y of t is equal to minus 5 by 2 x of minus 2 minus t. So y of minus t, that will give me x of minus 2 plus t. Okay, so now if I replace this by t plus 2, okay, t plus 2, t by t plus 2, okay, so be careful here, it's inside the bracket, minus 5 by 2 x of minus 2 plus t by t plus 2. So this cancels, x of t. So x of t, that is equal to minus 2 by 5 y of minus t minus 2. Okay, so if I had given this separately, then what I can write the inverse system as minus 2 by 5 x of minus t minus 2. This is the inverse system. Okay, this is the inverse system of this. So if I have given the integrator, okay, so this is the integrator, right? So if the ideal integrator is your system, so inverse system, it should be ideal differentiator. Okay, so reverse operation, right? This is your input. If I am applying it to this d by dt of x of t, I will be getting x of t. So this will be your inverse system for this integrator. Okay. So y of t d by dt x of t. Suppose this is the input now. Okay. What happens is, if x of t is a constant, so if x of t is equal to 6, this is 0. If x of t is equal to 4, this is 0. So it is producing the same output. So this will be non-invertible system. Differentiator is a non-invertible system. And it holds good in the case of discrete time system also, the same procedures. Y of n is equal to x of n by 2, y of n is equal to x of 2n. So in this case, it is nothing but the signal is getting expanded. This is nothing but the interpolation. Okay, it is upsampling. This is your downsampling. So in upsampling, I can recover the original signal. But what happens in the case of decimation or downsampling? The signal samples are lost. So if the signal samples are lost, then how will you recover the original signal? So this one will be your non-invertible system. This one will be your invertible system. Okay, y of n is equal to x of 4 minus n. This is also same procedure. We can consider 4x of 4 minus n. I will reverse this now. Okay, that will be 4 plus n. Then I will replace this by n minus 4. Okay, n minus 4. That will give you x 4n minus 4. This is equal to x of n. So this is y minus n. Okay, minus n plus 4. So we can say this is only the inverse system. X of minus n plus 4 is the inverse system of x of minus n. We can conclude that the amplitude reversal, amplitude scaling, time reversal, time shifting, time scaling, this does not affect the invertibility of the system. Just in case of discrete time system, what happens? It's like when x of an, when a is greater than 1, that is in the case of decimation or the downsampling, okay, that becomes your non-invertible system.